Hello, I'm Valerio Baiocchi from La Sapienza University, and I'm here to present our contribution on the geometric measurement of new Aniene and Claudia Roman aqueducts for flows estimation. This work is the result of a collaboration between La Sapienza University of Rome and the ELTA University of Budapest, Hungary. The construction of the aqueducts in Roman time was one of the greatest engineering works of that time. In Rome there were 11 aqueducts, and in this specific work we'll deal with the new Aniene aqueducts and the Claudia aqueduct and a small part of the Marcia aqueduct. The purpose of this work is to determine the flows in some of the aqueducts and evaluate if there are any correlation with variation in slope and geodynamic movement of the area. In 1917, therefore almost exactly 100 years ago, it was carried out another survey from the School of Engineering at the University of Rome. During the survey of 1970, a series of Orthometric benchmarks were materialized, which are described with a specific publication that we have tried to find. The inspection of a series of points described in the 1970 documentation made it possible to recognize the same characteristics currently present. For example, we can see here that is exactly like this situation, and so it was possible to survey exactly the same details. We decided to focus our research on the area between Porta Maggiore, that is near the center of Rome, and Capannelle, that is one area that is in the neighborhood of Rome, but still in the urban area. The length of the aqueduct in study is 10 kilometers. It is important to underline that this area, like the whole part of the Alban Hills, is affected still by coastal movements. In this slide, we can observe how the area that we have chosen, here in the red circle, is in any case affected by the movement of the Alban Hills, as evidenced by this study with INSAR technologies, where we can see that the largest displacement are here, where very recently some earthquake still occurred. After a careful inspection, it was decided to divide the survey into 3 parts. For each of these parts, a GPS and total station campaign was carried out. The survey was carried out over several days, with a total of 36 points measured with the total station and 15 points with differential GPS GNSS receiver. A total station of the Leica model TCR703 and the GPS GNSS dual frequency receiver model TPS PG-A1 of the Topcon were used. To estimate the height, each station used with the total station was also measured with the differential GPS GNSS receiver. Post-processing of the survey was performed with reference to the permanent station of the Latium region network framed in RDN 2008 realization. In this table, the points measured with the 8 plano altimetric coordinates. For the height, it was clearly considered the difference for the height of the phase center of the GPS antenna and of the center of the total station. Since we are considering the height difference in an aqueduct, it is necessary to know the orthometric heights. For this reason, the ellipsoidic heights obtained have been converted into orthometric heights by the geoid model ItalGeo 2005. That it has an estimated accuracy of 3 centimeters. Found in this way, the orthometric heights of each point measured with the GPS receiver, it was then possible to calculate the orthometric heights of all points on the aqueduct measured with the total station. Accordingly, in the table we can see the planimetric coordinates and the heights of all the points measured on the bottom of aqueduct channels. With the accurate coordinates of the single points, it was possible to calculate the gradients, both in terms of geometric distance between the points, as well as in terms of distance along the aqueduct paths. As it is well known, these two aqueducts flow one above the other at a more or less constant distance of about 3 meters, which is equivalent to 10 Roman feet. At point 13, however, that we have highlighted here in red, the difference is significantly greater, about 3.65 meters, equivalent to about 12 Roman feet. This cannot be due to the subsequent modification, but was an intentional modification of the builders who probably made it for slow down the flow in the upper aqueduct. To obtain a more accurate view of the gradient related to the currently existing position of the aqueduct, we realize this graph in which the highlighted area have aqueduct remain still existing. In particular, the section 13-17 still exists with a practically constant gradient, while other deformations can be observed on point 3 and 6, 7, and 11. Sections 2, 3, 6, 7, 8, 9, 10, 11 have an inverse gradient. This cannot be the effect of only subsidence, but probably a phenomenon related to the regional crustal deformation field. In this image, we can see more clearly that the deformation field hypothesized for this area may have caused precisely this type of deformation, with the inversion of the slope of the individual section of the aqueduct. Furthermore, the deformation and the general lowering of the area was also highlighted by comparing it with the survey of 1917. To do this, it was estimated that the difference in the altimetric reference system was approximately 45 centimeters. Considering this difference, it was possible to estimate a decrease in the last 100 years of about 3.9 millimeters for each year. The evaluation of the difference between the two altimetric reference systems was calculated on the basis of the few common points taken from 1917 and the current one, and also by considering a map of the same period of the Istituto Geografico Militare, IGM, and then going to verify the known points with the present known heights. Based on the survey data, the possibility of reconstructing the flows within the aqueduct itself was verified. As mentioned, the trend is very variable, so it was decided to consider only the slope of the longest and most undisturbed continuous section. The flow estimation models were based on an already published work by Stephen Monk of 2030, so we considered the total filling of the channels and the consistency of the transit section with the rectangular section that we see here in the figure. In this slide, we can see very quickly the difference between the flows calculated with our evaluation and the model report in the literature. To obtain the flow values in this case, it was therefore necessary to use the values of the velocities and the degree of filling of the channels in which we observed the points where it was estimated as regard to the aqueduct New Aniene. Here in details we can see the points used for the estimation in this aqueduct. In conclusion, we can say that the calculated values that we can see here for the two aqueducts are very close to the values of 2 on 1000 described in the reference text, and in particular we have obtained 1.9 on 1000 for the Claudian aqueduct, so very near, and 1.36 on 1000 for the new Aniene aqueduct. These slopes have allowed to define the water runoff and consequently the size of the channel in which such water flowed. These flows of water reached into the city center, gradually slowing down until they reached the center itself, with a flow rate for both the aqueduct of about 200,000 cubic meters for days. In details, we can see that our estimation is a little higher for the new Aniene aqueduct and a little lower for the Claudian aqueduct, but both of them were around 200,000 cubic meters per day, and so both of them were 400,000 cubic meters per day. The general lowering of the area was actually studied both on the flow, as we showed here, and on the base of the 1917 survey of Professor Reina, considering a difference in height of 45 centimeters between the two Orthometric reference systems that were in use at that time and that are in use presently. With this, we were able to understand that there was a constantly movement of the area till present. That is still demonstrated that by very recent earthquake in the area of the Albanil, like the earthquake of the city of Lariano that was some days ago. This is all. Thank you for your attention.